We're going to talk about network security today. It's an interesting pillar in security, and it allows us to protect systems against attacks even outside of the systems. Right? If you think about it, we talked about software security, which makes sure that the software itself is secure. We talked about host security, which makes sure that the host itself is secure, updates and whatnot. Network security now goes one step further and prohibits bad packets from actually reaching the potentially vulnerable host. Right? So if you think about an onion where individual layers help protect the system more and more, all come together, and the more outside layers of the onion are things like network security that allow us to protect the perimeter and outside of the regular attack surface. Learning goals for today, like understand what network requests are, like kind of complementary to the different network classes that you had. I don't expect you to know the TCP IP specs or any kind of protocol in detail, but we're going to go through a bunch of examples following standard protocols and then try to understand their security implications and the security trade-offs that were made. We're going to learn about firewalls and intrusion detection systems. Those have been around for a while. We'll try to talk a bit about trade-offs and whatnot, and data protection best practices to round all the things off. We have a bit of a longer outline today, starting from protecting the network, which is looking at the network itself as its own entity. And it's also something that you're likely not as aware of as, like you're very much aware that you have a computer, right? You've got a smartphone. You've got some other connected devices. Like you're very much aware of all of these devices, but the network is somewhat in the background connecting all of your different devices. Be it over Bluetooth when you're connecting with your smartwatch or other kind of IoT systems that you may be having, or be it over Wi-Fi if you're talking to your printer, to the internet, to some other like storage server that you have somewhere in your home, or any kind of other EPFL services that you're using. Right? So the network kind of provides these services, and the network is not just magic. It's not just a single hop, right? It's not just you're talking to one other computer, but it makes it appear as if you're directly talking to this other computer. But in the background, your traffic is likely routed through a bunch of intermediaries that need to be secure. So we're going to talk a little bit about these intermediaries. Remote access, perimeter, like the outside, network connections from the outside and how they interact with the current systems, such as firewalls, breaking larger systems into smaller and individual zones, firewall rules, what proxies are, different kind of filtering agents that can protect your system against attacks. IDS, already mentioned that. And then talk about workstation, best practices, how to look into the past or leverage insights from the past, such as logging, and to protect data. We're going to talk a little bit about backups. Now, you all know that breaches are pretty, like it's standard, right? Hacks happen every day. There's a lot of attacks being publicized every day. For the German-speaking folks in the class, there was today there was an announcement that one of the bigger German energy providers has been hacked and all the data is being sold. And I think like you can pick any arbitrary day. This is just the story of today, but you can pick any other day where like some large provider will be hacked with thousands, hundreds of thousands to millions of data records of people being breached and sold somewhere on the darknet. The example that I'm picking here is a bit older, like it's 10 years old by now, but it kind of demonstrates the effects, and it's nicely documented. That's the reason why I'm picking it. So if I would take a more recent attack, a lot of the questions are still open. There's still a lot of uncertainty. But with the target hack, this has been very well studied and very well documented. So it serves as an interesting example, even it has been about 10 years ago. These supply chain attacks are still kind of similar. This is a typical supply chain attack, and this is usually the standard example that is being brought up for any kind of supply chain attack. Because a supply chain attack means that you're not your software is attacked directly, not your system is attacked directly, but somewhere on the supply chain to your company, there's an attack happening. And in this example for the security breach at Target is like the Migros or Coop one of the Migros or Coops of the US. For perspective, their systems were breached through an additional third-party system where attackers installed some malware in their payment system and then over quite a long time funneled off data, payment data, customer data, and other kind of transactions through this third-party system. Right? So this was not directly Target's fault, but somewhat indirectly because they were using this vulnerable third-party provider that then exploited the data that Target had without actually attacking Target. Right? As a note for you, an attacker always attacks the weakest link that they know of. Why should they target the strongest link where you put all of your efforts into to make it as hard as possible for them to breach? Right? An attacker will evaluate your system, including all the components that are accessible, including any kind of third-party providers, outside providers that you're using, and then will attack the weakest link. Interestingly, here the security alerts, the security logging system alerted the administrators 2 weeks before the company actually started to react. And as a result, there were a lot of credit card numbers being stolen, and a whole bunch of people got new credit cards in the process. Right? Because all of these credit cards had to be renewed and exchanged, which also results in a cost. Now, another takeaway note here is that breaches will happen, right? As you're working with real systems, you have to assume that an attack will happen at one point in time. The question is how to react. And apparently, like many other companies, Target didn't have the necessary processes in place to actually react. Right? When the security system triggered and alerted them, they did not have best practices or protocols in place, but they had to develop them firsthand and even bring in external companies to actually help them analyze the damage and then secure it, which takes a lot of time. And this amount of time that was taken also vastly increases the cost of the attack or of getting rid of the attack. So yeah, this was an interesting case study. I encourage you to read up on the article, especially as it's going to be used throughout your career as a prime example of a supply chain attack. Now, when you're working with network security, there's usually an inside and an outside. It's in the most simple possible ways. Like if you're inside the network, you do have some trust, you do have some expectations about the users, potentially are authenticated, potentially they are logged in or whatnot. And inside the network, the goal is to segment the network, at least physically a little bit, right? So the idea here is to break the network into some individual segments and then tag each part of the segment with a certain access rights, privileges, and whatnot. And in addition, inside we often have what we call, or what is classically called, the DMZ, the demilitarized zone, to kind of expose anything that faces to the outside. And this also allows us to split. Right? Any server that needs to communicate with the outside internet needs to be placed in the DMZ, because otherwise there are going to be firewall rules in place that prohibit any access outside. And this also allows us to detect any kind of rogue access that is happening. Towards the outside, we ensure that there's secure communication, such as like if somebody from the outside wants to connect with any kind of services that we provide internally, such as a remote worker or whatnot, or a customer or some other interface, we leverage, depending on the access needs that they have, TLS, VPNs, such as IPsec or whatnot, to kind of protect the data whenever data is on the outside. Now, what you see here is towards the outside, we assume secure communication, that all the data, all the communication that we have is encrypted. This is common best standard because there's enough third-party entities that enjoy listening to any kind of communication that happens to the outside. Now, more and more, we are also moving towards fully secure communication towards the inside, as in any link between any two computers should be encrypted. On one hand, this allows us to push the zero trust primitive, which we're going to hear about in a little bit. On the other hand, this also assumes that maybe there's an attacker somewhere in our network, maybe a rogue device, maybe a rogue agency that has had access at one point in time. This kind of prohibits this parameter as well. So in addition to segmenting the network physically, we can also enforce secure communication inside. Now, I brought up a couple of terms here. Secure communication, you already know. Segmentation is something that you have heard in another context about compartmentalization. It's kind of similar in networking. Network segmentation kind of takes the overarching network and breaks it into individual pieces, right? So we make a plan of how the network should look like, what the different departments are, what the different actors are, and then kind of break this into functional zones that make the most sense. And then we can manage access and interactions between zones using some form of access control list that we enforce in routers, firewalls, or whatnot through an overall configuration. Now, these don't need to be done manually, because especially updating would be a massive pain, but there's tools and systems out there to actually manage those. The key idea for network segmentation, or the key benefit of network segmentation, is that it prevents an all-at-once compromise of facilities. Because otherwise, if the attacker would compromise one single computer without segmentation, they would have full access to all the other computers out there. Let's do a simple example. We have help desk and HR. Right? Help desk, somebody working in the help desk may not be as educated as about security as somebody working in HR, because in HR they're working with highly personal data. So these data is much more valuable. Like the help desk person may be working just on a script to answer simple requests about a product, right? Now, if the help desk person clicks on a link and installs malware on their computer, this may result in them, without segmentation, allowing the attacker to access any kind of private data on the HR systems, right? While segmentation will kind of break these two systems apart. Similarly, as a developer, you should not have access to all the HR and payroll data, because there's just no need to share everything internally. So access from one zone to another should be controlled by access control lists, which are then pushed to firewalls or router. One classic way to implement network segmentation is rings. That's the textbook implementation. You have rings where the most internal ring is the most privileged one, and usually implements things like authentication, management, authorization, user management, auditing, any kind of like the most privileged services they have. And then you go one ring after the other towards the outside. There could be critical systems such as HR or legal, finance. Like one of the most critical things for many companies are that we have to pay our salaries once a month. If all the computing systems go down, no salaries go out, and then the poor employees suffer. Right? You don't want that. Same for finance and compliance. If you're not paying your bills, a lot of bad stuff can happen. Then there's going to be internal firewalls between each of these rings, user systems, internal services, external services, and so on, right? One ring after the other. That's a classic view of network segmentation. In practice, there's often, you can often do a full hierarchical breakdown where one layer always has strictly more properties than the next layer. And this is much more separated. In practice, it's much more like a jigsaw piece, or like a hypercube, an n-dimensional hypercube that is sparsely connected. For the DMZ, right, the demilitarized. Go ahead, question.
What does isolation between the three? Because, for example, you cannot isolate everyone from getting access to authorization server. So everyone needs access to the most core link in this key, and that's why I don't know.
So they may be allowed to access through the internal service, that then has an access right to this more internal one. Right? Maybe one port is allowed to connect. Like you can allow connections from the outside to the inside through the firewall. So for example, like if there's authorization and authentication in the innermost ring, the finance system needs to authenticate and has user access and identity management services that allows it to punch through. Right? So when you're logging into the innermost ring, and then with the token you're continuing to the HR system or whatnot. So it doesn't mean that nobody has access to it, but the access is tightly controlled to whatever services it provides. So you cannot directly access the, file system of the authentication server, right? But you can access the service that it exports. That makes it clear. So again, this is a concept. As I try to explain in practice, it's an n-dimensional, sparsely connected hypercube, which makes this a bit more, with the sparse connection being like some service that is placed in the finance system needs to connect to authentication services to one aspect, such as authenticating a certain user. Right? But it doesn't allow connections to all the other services. Right? So you cannot log in as root on this privileged server because SSH access will be forbidden, for example. Right? So you can still tightly control the interactions to the internal services. So while some and not all the external services are allowed to, maybe only the finance and user and systems are allowed to connect to the authentication service. Right? Only systems placed in this ring. So it still makes sense, but it's hard to fully separate the individual parts, as you just mentioned, because you still need services. Otherwise, if you cannot provide services, there's not much you can do. Right? It cannot be just contained in itself and not do any kind of computation. Cool. Other questions? So the DMZ is a physical or logical subnetwork, right? That kind of separates whatever the organization wants to have facing towards the outside, such as the internet, right? The external network node can access only what is exposed in the DMZ. Classic implementation of a DMZ is a double firewall approach, where you have one firewall for whatever is going in, and then a second firewall that allows you to access the internal services. Now, in the DMZ, you have things like the web server, the mail server, and the VPN server, and some of these servers are then allowed to punch through. For example, the VPN server may be allowed to access some kind of internal services, such as services by the finance department or whatnot. So if somebody, either like an external branch or a remote worker is trying to access their services, they need to establish an internet connection to go through the first firewall to the VPN server to then punch through to the internal services. Whereas somebody from the outside who is not logged in through VPN can only access the web server and the mail server, but the mail server may even access data on the file server to share attachments or whatnot, and the web server may connect to the database server or whatnot. Most common services in the DMZ are web, email, DNS, and VPN service, because they make most sense, right? Usually a company wants to expose those to the outside. Very likely you want to send email to the outside, therefore your email server needs to be in the DMZ, because you're not just interested in internal email. Same for web. There's an intranet and the external network, and all of these different parts need to be connected together. Now, one approach for network segmentation, an alternative approach, is zones, which kind of goes more into the practical approach, where you have different kind of containment zones. Like you think about how to logically break down your different departments inside a company. So you break this into developer zone 1, developer zone 2, external zone, production, user, corporate services, and whatnot in the internet. And between each of these zones, you have a firewall in place that restricts the communication that is possible and that is allowed. Right? So this highly limits how the different services can interact and requires explicit permission to go from one to the next. But it highly limits the exposure that all of these services have. Right? So even if there's a mistake in configuring some of the internal services, there's still protection against any kind of outside attack. So this is the damage is being restricted to other internal users and internal services that are nearby. The key challenge here is creating firewall rules for each case, as it's extremely challenging to keep everything correct, updated, and then continuously synchronized with all the changes and mutations that are happening inside the company. And this is almost full-time work. You need to clearly document all the different zones, all the different connections, and then put an effort into keeping all of this in sync as you go along. Now for the demilitarized zone, there's kind of two different configurations, the single firewall or the dual firewall configuration. The single firewall is that the firewall has kind of 3 outgoing networks, one to the internet, one to the DMZ, and one to the corporate network. Whereas with a single firewall, the firewall is a single point of failure. Right? If a firewall is misconfigured, some attacker will be able to access the corporate network by just going through a single firewall. Versus the dual firewall has the benefit that there's a firewall from the outside internet to the DMZ, and then a second firewall to any kind of internal services. Now the benefit is that you get this additional layer of protection. You need to screw up 2 things at once for an attacker to gain access. The disadvantage is additional latency. Each additional system you need to go through adds latency to the communication, adds additional cost to the communication, and you also need to keep 2 firewalls up to date. So there's a trade-off between the 2 parts. Right? The single firewall may be faster, may be cheaper, may be easier to document, but higher risk of failure, whereas the dual firewall can be more secure but requires additional effort and work. Now, this kind of finishes the discussion about the demilitarized zones. What you would think is that now we have seen all of these different parts, right? All of these different networks, and it's a lot of different connections that would go between all of these different services. What you can do instead is a form of virtual segmentation, because otherwise you would be required to have hundreds of different cables. You don't want to have an individual cable for each connection. Ideally, you want to route through the cable whatever is being correctly accessed and correctly needed. Network zones differ from physical zones. For example, the HR zone may span 2 buildings because there's an HR person working in building 1 and in building 2. So we have this logic separation based on the function of what people do and the geographical separation to where they sit. Right? And we need to match the 2. Now we could have a lot of cables and then make sure that we connect the right cables to the right things, but this is kind of challenging. So what we usually resort to, also because it's much cheaper, is to have a few cable and then virtualize on top of the cable. One aspect would be virtual LAN or VLAN technology, where we compartmentalize several layer 2 networks, such as the HR zone, the development zone, and a bunch of other zones, over the same cables and switches, and any socket in any building can then be configured to belong to any layer 2 network. So this means that, for example, on the backbone, we have all the traffic going through, but encrypted and tagged or with other layers foreseen. Virtual routing and forwarding, VRF, allows a single router to be part of several IP networks with VLAN and VRF, which then allows you much more tighter control of any socket in any location and configure it. For example, this office, this socket belongs to the HR, this socket belongs to the development zone. Virtual machines are also a virtual form of segmentation. It allows coalescing several servers and routers on a single hardware rack. For example, the web server in the DMZ may actually be running on the same physical machine as the database server of the internal backend zone, right? Depending on your configuration and your security analysis. You likely don't want to do that due to side channels, but that's a risk, or depending on your configuration, this may be a risk you want to take. Now for a quick discussion, how and where would you implement VLAN segmentation? Let's assume Ethernet for now and wired internet. Like, how would you implement VLANs? How would you implement over a single cable or a set of cables having this separation? Any thoughts? Go ahead. How would you implement it? This replaces a bunch of routers. This replaces a bunch of cables, right? So now we need to somehow make sure that over the same cable we can have multiple networks. We can have multiple zones communicating with each other. Like, how would we implement this? In the simplest form, we just we give everything a different IP address, right? A different IP subnet, if we're talking IP, and then just connect it through the same cable. Is this a good baseline, right? So this is my hypothesis. I implement VLAN by just giving different IP addresses with different IP subnets. Is this sufficient? Yeah. Again? Yeah, the switch can help. I think the switch is part of the solution because this allows you to route and make sure that the certain traffic only goes to one target. What if I do ARP poisoning? For those that know. Like I suddenly get the network packets through the switch from another system that I'm not supposed to, right? Also for let's say we don't have a switch, we just have a hub that distributes all the packets. The key issue of the IP-based solution that I just mentioned is that all the packets just go to all the different endpoints, and anybody that just sniffs on the network could listen to everything. Yeah. I was giving an example how you could implement it, right, with the different IP subnets, and a hub that it wouldn't, like somebody could sniff, and that wouldn't work. So a switch is needed as part of the solution. What else? Yeah. So, some access control lists. Sure. What else does the switch need? Yeah. And you likely knew this before, right? So one cool approach is the current implementation, or the implementation is that each Ethernet frame gets a tag. Like, this is the VLAN it belongs to, and then the switch knows, hey, like at this port I have VLAN 15, therefore I only forward packets with VLAN 15. At this port I have VLAN 12, so I only forward packets of VLAN 12. If it's a packet for a different VLAN, I just reject. Right? And this allows you to implement virtual segmentation. Cool. So you add a couple of bits. It's the same as with everything in computer science. Just add a layer of indirection, and you can solve any problem you want except for the problem of having too many layers of indirection. So what I already mentioned before are zero trust networks. I think this is one of the newest hypes around network security. And the idea here is that you assume that all the different components are broken and you don't trust any other component, which means that every endpoint needs to be sufficiently secured. So the base assumption is that you do not trust any internal machine or other machines whatsoever, and you try to prevent any kind of lateral movement. Because usually if an attacker gets a foothold on a single system, they will be moving laterally. If they have access, like user access on one system, they will try to get access on other systems as well, because there's other files, other data, other systems on these other machines that they can target. So the idea of zero trust networks is to continuously monitor and validate everything, no matter where it comes from, even if it comes from more privileged services. Install local firewall on internal machines, which gives you least privilege and access control to some extent. And then what I just mentioned before, encrypt all traffic between internal machines, which implements some form of microsegmentation, allowing you to protect against any kind of sniffing attack, even if VLAN fails, for example. And this allows you to ensure that even an attacker that sits on your network or near your network cannot get access to it. And then strong authentication, even internally, such as multi-factor authentication. Except if you're implementing it in the way that EPFL does, where I have to enter my second factor about 15 times a day, which annoys the hell out of me. Which is also a lesson in usability for security, right? Your security solution needs to be usable, which brings up things like session lifetime or token lifetime. And a general accepted notion is that if you annoy users more than once a day, this is too much, right? You can ask for a second factor once a day, but if they stay on their same system, you shouldn't renew the second factor. But this is somewhat orthogonal to the zero trust angle here. Because in the end, it's a trade-off, right? How much is the additional cost for the time users spend entering second factor versus the cost of a breach? Because remember, you will be breached, like attacks will happen no matter what you do. And in the end, it's all a game of probabilities. It's a game of poker where you calculate the risk versus the potential reward. And you're trying to make sure that the security benefit that you get is sufficient to deter attackers, but also to keep your business going. Now, zero trust, to go back to this topic, requires additional work to configure machines. Now, we do have a lot of modern technologies available, such as Docker, Kubernetes, whatnot, that allows us to automate a lot of the configuration. There's less work on configuring the network, as we can just create rules automatically and roll them out, and also reduce the impact of any kind of compromised machines. If you want to read more, here I've got the link for you available. We're going to move on to VPN, protecting remote access. And here the idea is that somebody outside of our network would like to get access to our internal network. And a way to implement this is through a VPN. VPN runs a private virtual network over a public physical network. So again, similar to the idea of the HR zone being, the HR people being in two different buildings, we have a virtual network that is supposed to be one unified network over multiple distrusting places where we are routing the information not over a trusted network, such as our network, but over an untrusted network being the internet. So we require encryption to keep it private and confidential, and then we're encapsulating IP packets inside IP packets to hide all the internal addresses and the internal data. Distant network or single machines can access a VPN through the VPN gateway, and then your laptop or whatnot can run VPN software to create a virtual network interface, and all the traffic that is being sent to this virtual network interface is then being sent to the virtual private network. Before the packet is sent, it is encrypted and encapsulated with an IP header and the public address. So let's look at the physical view, right? Here we've got the remote employee at the top left. We've got the internet. We've got the Geneva office and the Zurich office. You see the IPs 10.1.0.2, 1.0.3, 2.0.2, which gives us the two different offices. So Geneva is 10.1, Zurich is 10.2. These are internal addresses that are not publicly routable. We are also seeing their public addresses. So Geneva is the 42.21 public address, and Zurich is the 132.2 public address. And we see the remote employee with the 80.32 address. Now, the physical addresses are required to go from remote to Zurich, Geneva, but cannot reach internal services. Right? So if you send a packet here, we can go over the internet. The packet can go to the Zurich office, but that's pretty much it, right? It will only end up at the router. Now, if we turn on a VPN and we configure a VPN, in addition to our public address, we also get an internal address. So we are the remote employee that now turns on the VPN service, and we get a virtual address, for example, 10.3.0.5, which positions us in the remote office area, for example, right? And we are being routed through the VPN between the Geneva and the Zurich offices. Now, the virtual connection is overlaid over the physical connection, and packets are being encapsulated in here. What we see here is we have in blue the internal destination and the internal source, right? But if you would send this to the regular internet would just drop the packet and tell us, hey, your IP packet is nonsense, right? It doesn't work like that. I have no idea how to route this, because the routing information, the 10.1, 10.3, is only valid internally, right? It's only valid inside our company, inside the network of our company. So the VPN allows us to bridge from the internet into our company network, right? And the VPN software knows that, well, the destination address is the Geneva router coming from us, right? So over the internet, we're using the first two packets to route. As soon as we end up at the VPN server will unpack the IP packet and then continue the routing internally to correctly deliver the packet. So let's look at an example, right? We have our internal packet here that we want to send to a service. As said, the VPN server needs to encapsulate it. So we wrap it into a regular IP packet that can be routed on the public internet. That's the red IP packet that then contains the blue IP packet inside. And it is being routed over the internet, right? And here, the server, the VPN server sees, oh, very nice, you're sending a packet to the VPN service. We're going to unpack it and then forward it internally to this system. And all is good and nice and works. And we have bridged the remote branch with the Geneva office, and the two can send packets between each other. On Linux, you can use the IP command to show such network configuration, such as IP address show, and then you see the Ethernet address of your card, the internet address that was configured, and as you see down here, you see WireGuard. This is the internet as configured before that is going through the VPN. Now, if you are connecting to any internal service in this network, the routing cables on your Linux system will be set up so they can go through this internal system, right? You've got the physical network interface with the public-facing IP address, and the virtual VPN interface is your internal address. Anything you send to this internal address is being packaged by the VPN software on your system and then being sent out on the external one. You can look at IP route show, which then shows all the different routes that are being installed. And here in this example, the route 10.1.0, all the packets in this subnet are being sent to the WireGuard network, which serves as this bridge. Typical protocols For VPN are IPsec, which is the official standard. OpenVPN, which is an open source software based on TLS, which implements a TLS connection to encapsulate the IP traffic. WireGuard, which is built into the Linux kernel, gets a very nice speed. And then you've got a bunch of proprietary protocols such as Cisco AnyConnect, Microsoft SSDP, and whatnot, which give you a nice visual graphical user interface to configure and make maintenance a bit easier. EPFL uses Cisco AnyConnect, if you've been wondering or using it. So typical uses of VPNs are allowing remote workers access to internal company networks, interconnecting different company sites over the internet, because it's much cheaper to have 2 internet connections than a dedicated line between the two companies. For us, accessing university resources. For example, I'm using the open source hack that re-implements Cisco AnyConnect on my system to access papers when I'm at home, because the publishers are blocking access to papers otherwise. The CTF teams are using it also for playing CTF and bridging networks between teams. So whenever we go to DEF CON, we need to set up a bunch of such WireGuard rules to set up the right connections and networks to play the CTF. VPN for privacy, right? That's one idea. Some of you may have heard, and I've added those slides after like half the YouTube ads started spurting and selling VPNs for privacy, which is utter bullshit. And I would like to highlight why this is bullshit. Right, so let's say you have you are paying 80 Swiss francs a year for VPN so that you have private access to the internet, or so you think. So what it does is you're trying to access data in another country. For that, it works really, really well. Right, you're encapsulating the packet, you're sending it here, right? And then the VPN provider in Geneva unpacks it and then sends it over, right? So the external service sees only the address of the Geneva office, right? They cannot identify you directly. But your VPN provider now knows all the websites you browse to. Now, whom do you trust more, right? The VPN provider that collects a lot of data across all the people that want to surf privately, or just your internet provider that has a very broad set of just all the different browsing behaviors, right? So from a security perspective, from a privacy perspective, I personally would not trust the VPN provider. I don't trust my internet provider much more, but it's a different story. But selling VPNs for privacy is bullshit. So yeah, but it's in the end, the only thing you're hiding is your current IP address, but the VPN provider likely keeps massive logs of when you logged in and what you did. So the VPN provider is now an additional trusted party that you need to trust to not leak your data, in addition to all the other parties that are out there. We're now going a bit more into protecting the perimeter, where we're looking at any kind of external services and protecting access from the outside towards the inside. Right, we're going to be a bit more concrete about firewalls and configuration thereof, and how these different things are being connected. A firewall essentially enforces network-level access control, which means that it looks at each packet that is going through a network interface intently, thinks strongly about it, and then either allows it through or rejects it or routes it somewhere else. Right? So firewalls are typically at the border between internet and the internal network, with larger networks even having multiple firewalls and multiple zones and firewalls in between to separate them. Firewalls operate at the network layer, and they analyze all kind of metadata. Right? If you think about a network connection where data is being sent through, the firewall will look at packet headers such as the IP address, is it TCP, UDP, what are the source ports, what are the destination ports, has the connection been established before, should we allow these connections through, and whatnot. Firewalls are oblivious to the application layer for which the packets are transmitted. So a firewall doesn't care if you're doing a web request or if you're sending anything else. The firewall usually only cares what port, what service, what system you're connecting to and from. Protecting the network with firewalls at the perimeter is insufficient due to different kind of lateral movements the attackers can do. Propagation of attacks is prevented by additionally segmenting this internal network into different zones, as we have discussed in the first hour. One example could be the EPFL network segmentation, where most machines are just in the generic EPFL zone for all the different desktops that we have. All machines accessible from the internet must be in the untrusted zone. Like there's a special zone where we move all kind of services, be it a virtual machine that hosts some kind of service or another real physical server. They have to be in the untrust zone. Machines in untrust cannot connect to machines in EPFL, but opposite is okay because EPFL machines are allowed to connect to the outside. Data about grades and my salary are, for example, behind a paywall in the back end of the data center role. If you're interested in my salary, you can also look this up because it's public. The EPFL salary scale is public, for those that didn't know. Same as if you're interested in a PhD, postdoc, or other scientist, you can look up all the different salaries. Each zone can only connect to zones of lesser security, similar to mandatory access control that we had before. Now there's two slides that EPFL would like us to remove because they are now considering this, they're no longer as up to date, right? But in 2018, the EPFL network services released a few slides about the EPFL configuration, and here you can just have a look at how the different networks are built up and how they're being connected, including the different connections as example. And here you see the different zones that were established from outside, DMC, DC, untrusted, right? You're seeing the first three layers. This is going from outside towards the inside. I'm reading source top to down. And then you get more and more trusted services the further down you go. Zone EPFL and zone VPN are already rather trusted, and then we have some additional zones that are of higher privileges. Now, there's just an example for a configuration of different zones. Here you see based on functionality where you connect from. Do you connect from wired network, Wi-Fi, VPN? Are you from a trusted building? Are you somewhere going to the data center and whatnot? There's only a few of configurations. This will likely change going forward as we're moving towards more zero trust, with adding a couple of additional layers. But you see that even for somewhat initial configuration, the number of zones can look quite complicated, and it can be quite involved to keep all of these different rules up to date and to keep it synchronized and whatnot across all the different routers and systems and servers on campus. Now, for firewall rules, when you're writing them, the default is to use an allow list and not a deny list. So what's the difference between allow and deny list? And a deny list is, I'm looking at all the traffic. By default, everything is allowed. I will deny traffic from here. I will deny traffic from there. And I will deny traffic from there, which requires you to enumerate all the possible bad sources. This is not a good approach. Like you want to do the inverse, like you want to do an allow list. By default, you should deny all traffic. And then you enumerate all the traffic that is allowed. For example, in this list here, from an internal network to the external network, over the protocol TCP, ports 80 and 443, we allow it. What are these two ports? Yes, HTTP on port 80 and HTTPS on port 443. We also have a second rule from external to server, TCP port 22 that we allow. What is 22? SSH, exactly, right? So we're allowing one internal connection, and maybe we have a couple of web servers as well, where we will explicitly allow it. Now, in the configuration of virtual machines that are running somewhere in a data center, you can also define what kind of services they are running. Like, should this server be running a publicly routed web server? If so, this will allow the administrator, through a simple click, to simply set all the necessary firewall rules that this gets updated in all the different other targets. The final rule in any allow list will be any, deny, denying all other traffic. And this is exactly why we need default deny. No bicycle riding, rollerblading, roller skating, skateboarding, scooter riding, but it doesn't say anything about unicycles, right? Cool. So firewalls work at the network layer, looking at network packets and network streams. If you move one layer up on the network stack, we will look at applications and at the application level. And this is where proxies come into play. A proxy can act as an intermediary between the server and the client. So it acts as a server to the client and as a client to the server, right? For example, the proxy can terminate the connections that we submit to the internet. For example, in the upper configuration, a web proxy could terminate our connections and then cache different files. Let's say you're in the business of installing lots and lots and lots of Maven packages, and you want to make sure that these packages are nicely cached, so you don't hit the public service all the time. So you install a proxy on your end that will cache all the different targets, so that if you have it in your cache, you can just return the cached copy. That's one of the system's benefits of a proxy. A reverse proxy is closer to the server. Like we see the two options, proxy and reverse proxy. Proxy is on our end. For example, we are a company. We have a web proxy that caches some of the common files. A reverse proxy is for the company. So if you as a company, you see that every time somebody connects to your web service, you're firing 15,000 SQL queries to the server, and you're bringing it down to its knees. You're trying to offload some of the heavy load by caching some of the replies on your end, so that if the same request happens right afterwards, you can just serve the same request. Right? The reverse proxy offloads reduces the load on the server against the users from the internet. Reverse proxy also allows you to prioritize. Let's say you've got 3 tiers of paying customers. You're being DDoSed. You are immediately shutting down the free tier to provide service to the paid tiers, for example. Right? This would be one possible solution to that. So web proxies, to go a bit more into details here, protect users surfing the web against threats by reducing attack surface, because web proxies from a security perspective can do more than just caching. They can analyze all the data downloaded from the internet, so for example attachments or whatnot, and also block access to potentially dangerous sites if they detect that an exploit is running or whatnot. The browser must be configured to use the proxy, and the firewall can be configured to only allow the proxy to access websites, and users cannot surf the net if they don't go through the proxy. Right? So this is the good configuration of a web proxy. So the firewall will say deny all traffic to the internet on port 80 and 443, and if somebody inside the company wants to access the internet, they have to go through a proxy. The proxy analyzes all the different requests and makes sure that the connection actually works well and everything is okay. Now for HTTPS, right, if you want to hide the proxy, like one approach is hiding proxies. So you may want to hide the existence of a proxy and do a transparent proxy by just having the network traffic redirected through a proxy, and then the proxy does its thing somewhere in the middle, which works really well for clear text connection, but for HTTPS, you end up with the issue of having to man in the middle connection. Because if your web browser does TLS handshake with the other party, the proxy would not see anything anymore, right? The proxy can be configured to intercept HTTPS traffic. Rather than forwarding the handshake itself, it pretends to be the server, which in its default configuration would make this hard because the browser sees a fake certificate of the proxy, because the proxy obviously does not have the correct certificate for the target system. This could be solved by installing, if you're in a corporate environment, a fake CA that just allow lists the different targets and create certificates on the fly for all the different websites you're visiting. Or you can configure the company browser to accept fake certificates. Another option is to just pass through. By default, HTTPS traffic is encrypted. The proxy can just forward the TLS handshake between the client and the server and acts just like a pass-through, prohibiting the proxy from seeing any traffic. So the proxy only sees encrypted traffic and cannot filter anything useful. Now, web proxies for HTTPS, man in the middling is getting more and more difficult due to the different technological advances, such as HSTS, which enforces HTTPS after the first connect, certificate pinning for preventing certificate spoofing, perfect forward secrecy of TLS 1.3, and whatnot, making this harder and harder. So this means that a company can no longer transparently proxy your network connections, and you will require some other configuration, such as configuring a network proxy explicitly in your web browser, where such a setting is actually available. If you want to grab some popcorn, I encourage you to read this beautiful rant by Kenny Patterson, where he put the banking industry in place when they wanted a backdoor in TLS 1.3 for their legitimate purposes. Maybe as a side note, in security, if you ever put a backdoor in there for the good guys, also the bad guys will use it. There's no backdoor that only works for the good guys. This is just not possible, right? It just doesn't exist. So yeah, beautiful rant, go read it. Mail gateways, so mail servers are also a kind of a proxy. They act as a proxy and a reverse proxy. All outgoing mail is stored on a mail server because it has to store the mail until you're able to download it. And incoming mail, all outgoing mail is stored on the server and then forwarded from the server to all the other parties. And incoming mail is being stored there as well until you download it. Mail gateways, whenever they receive an email, they do a whole bunch of things, such as checking for malware, for spam, filtering, sender verification, and whatnot. They do a whole bunch of checks to protect you against any kind of phishing attacks and whatnot. Another aspect at the application layer is a web application firewall, or WAF. It's a typical example of a reverse proxy with the goal of protecting a web server against malicious requests from the internet. So think of you used the super cheap intern to write all your web applications and they're now full of bugs. Instead of actually investing the money and fixing the bugs, you just add an additional layer of security before that filters all the requests that go to the web application and try to detect if something bad is going to happen. Now, sarcasm aside, like all web applications will have bugs, no matter if they were written by an intern or not. The goal is to further reduce the attack surface. You should, as you have learned in the software security class or the testing class, that you should test all the web services that you run. But there will always be some bugs that remain. Therefore, the web application firewall in front tries to filter certain patterns, certain request patterns to further reduce the attack surface and make sure that you cannot be attacked as broadly. Web application firewalls typically look for cross-site scripting, SQL injection, They can filter or rate limit DDoS attacks by reducing the amount of responses you get, block IP addresses for a certain cooldown period, or also authenticate users. An example of a web application firewall is mod security, which started as an Apache module. Apache web server, for those that don't know, used to be the default web server that every single system ran. And the web server can be configured with additional modules, and you can load different modules that provide some extra services. And mod security was one of these service modules that started for Apache, but then grew out of Apache and is now its own independent project. There's a free and open source set of rules, the core rule set with thousands of rules that try to filter for SQL injection. Right? So they filter any incoming requests or any incoming data for union, select, from. So these are regular expressions, sleep, benchmarks. So this is like a direct SQL injection or an indirect one that uses timing as a second channel to send data. Cross-site scripting are similar examples through script, embed, or whatnot. But these rules can also be quite complex. For example, this rule here is an example of cross-site scripting attack in a browser. I personally do not like to write regular expressions like this because I'm 100% sure I will make mistakes in it, but I'm sure the people writing those are great and much better programmers than I am. But yeah, as you see here, these rules can become quite complex. And I'll offer a beer or other favorite beverage for whoever decrypts this in a couple of seconds. Web application firewalls can also be quite paranoid. So sometimes they overshoot. Like, for example, this is the message from Cloudflare. Sorry, you have been blocked. Who has seen this page? Why and when? If you can recall. Go ahead. No particular reason. Okay. Anybody knows? Yeah? Yeah, because somebody else will have run a DDoS attack against the website, for example. Yeah, that's through, if you use a VPN, this may be the case. I have seen this most frequently with privacy extensions. So if I block certain like side channels to Google, Facebook, Twitter, 400 ad networks and whatnot that the website is trying to connect to, sometimes you get blocked because the website assumes that it should be able to connect, and if you block some of the connections, they block you. Yeah, so sometimes they can be overly paranoid, or maybe this is part of their business model. Another backend, application level backend, is an IDS, an intrusion detection system. Think of this as a clever agent that scans all the traffic for all the applications to detect potential intrusions and potential attacks. It generates an alert if it thinks it saw an attack, and it can also block traffic, which is then called an intrusion prevention system. Like, it's not just detecting, but also preventing possible attacks. There's two key technologies. One of them is signature-based, whereas similar to the regular expression you saw before, you define certain signatures, and the other one is anomaly-based. You're learning the baseline profile, and you're detecting whenever something doesn't fit to the baseline that you have just seen. So what's the difference between an IDS and the web application firewall that we just saw? You've already answered twice. I'll pick you if nobody else raises their hand. It just alerts Well, for a prevention system, you could also block, right? So you could do the same. You want to go ahead? You're close. I would have phrased this a little bit differently. The web application firewall protects a web server. That's why it's called a web application firewall. It has extensive rules for web servers and anything that can happen on a web server. An IDS or IPS protects all the services. So it has rules for email, different systems that you're targeting, and it can include web application aspects, right? So the web application firewall is usually more involved, but exclusive for web applications. Whereas an IDS is broader, but often cannot go as deep. One of the key issues of IDS or IPS is that it has a lot of false positives, which means that the network security people will just drown in alerts. And it also has false negatives, right? There can be successful attacks that slip past this system. So if you look at a signature-based IDS, it just compares network traffic against signatures from a pattern database, just like a web application firewall does for web traffic. It requires knowledge of an attack to create a signature, right? So you have to know how an attack exactly looks like, which means that it results in false negatives for new attacks. And matched signature doesn't always mean a successful attack. For example, if I look at my like my personal website, I see about, I don't know, a couple of 100,000 tries for WordPress, Joomla, and like 400 other content management systems, whereas I have a single static website, right? Which means I don't even have these things installed, but I still see all the requests to these potential exploits, right? So I know that on my web server I do not have WordPress installed, but I still see accesses to, or like get requests on the server level to all these different vulnerable patterns, right? Which also hints at one of the disadvantages of IDS. It doesn't have context, whereas for web application firewall you could have context about the system itself. Right. So an IDS may also just alert the signature matches for a Linux vulnerability in traffic of a Windows server, right? So this also results in a false positive. Signature examples are high number of false login attempts, URL with lots of parameters, exploiting a specific vulnerability where you hard code the actual vulnerability type. But there's a bunch of different rules that are possible, and there's lots of companies out there that try to sell you a lot of these sophisticated rules, and this is a pretty big business out there. And then they also sell you a second service where they filter the false positives down to a reasonable level that you can actually respond to. So you can make money twice. Amazing, right? Great business model, the security thing. Snort is one of the IDSs that is most well known. Snort sniffs traffic in front of your firewall to detect potential attacks. Right, so it looks at all the traffic going through, sends alarms and updates to the firewall, potentially blocking the attacker. There's large databases of different rules. There's a commercial database of some additional rules, and you see that this was being acquired for $2.7 billion, right, a couple of years ago, which is quite expensive, and had around 600, 700 employees back then. If you look at Snort as an example, right, this rule detects an infected Android phone that connects to the attacker's server. You see that the message will be malware CNC, command and control, access Android Trojan, variant outbound connection. It scans for update, up folder, update fun, function.php, content is dalvik / blah, 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 blah. different kind of HTTP header it matches and whatnot. You see that this is HTTP only. Again, here's the potential issue of encrypted TLS traffic in corporate environment that makes this a bit harder. So this much about signature-based system. A quick note about anomaly-based systems. The goal is to detect unknown attacks using an anomaly-based system. And here the design is rather simple, right? You run the system for a while. You record all the traffic based on whatever metric you want to record. And then as soon as you go from training mode to enforcement mode, you're looking at, do I see anything that I haven't observed before? And then you throw an alert and terminate the connection or whatnot. So the concept is rather simple. You look for unusual package, growth in port scans, growth in changes or whatnot. This might not detect an SQL injection because the amount of data that is being sent to the web server may be the same. It may look like a perfectly benign request. But it may notice a 200 megabyte transfer of password hashes from the database. Because suddenly the response from the database is not just 2 kilobytes, but 200 megabytes that is being sent to the attacker. Right? So you can detect very severe anomalies. But it also generates a lot of false positives because an anomaly may not just be an attack. It may also be, hey, the developer installed a new version of this software, which is different. Right? And especially in a somewhat agile environment where you're constantly changing services, constantly adding features, constantly changing code, anomaly-based systems have a really, really hard time fighting against this signal-to-noise ratio. Right? And now one of the key issues here is that we are kind of prone to the base rate fallacy for all of these alert systems. Now, the probability of attacks is very, very low. Right? Let's say 1 in 10,000, or 1 in 100,000, or 1 in a million. Right? The probability of a real attack is really, really low. False positive rate of an IDS can be 1%. False negative rate can also be 1%. So you may be missing an attack with 1% probability. You may be missing some of the information, or just the configuration is not there or whatnot. And let's say, given these parameters, it's 2 a.m. in the morning. You receive an alert from your intrusion detection system. Is this a real alert? Do you really need to get out of bed? Right? And the answer is it's very hard to detect. Right? If you have a false positive of 1% in a single packet, this for extremely rare events, this massively amplifies because we have so many true packets that go through, so many benign packets that go through, that will always have way more alerts than false positive alerts than real alerts. So the true positive rate is 99%. The probability that something is malware is highly improbable, and something that is marked as malware is the 1%. So the probability that something is malware and marked as malware is slightly less than 1%, which means that depending on the situation, you may still want to get out of bed, like if you're working in a high secure environment, but highly likely this is going to be a false positive, which also means that it's extremely challenging for the network administrators to keep track of all of these messages due to the base rate fallacy. Like, the amount of bad traffic is so low that any mistake in classification is just going to cause so many false positives, right? Because you have so much more benign traffic that is going through. Like, even a very small false positive rate is going to cause massive amounts of false alerts compared to the few real alerts that you are seeing. And that's a key issue when we're looking at at networking, intrusion detection systems, and so on. Protecting your workstation. Next step, we're going to change gears a little bit. We're now going to look into like from the network to whatever happens at the workstation or at the desktop or laptop level. So we want to keep our systems updated and secure. We want to prevent as many exploitable bugs as possible. Therefore, automatic updates is a no-brainer, both for the operating system and the application. Like 10, 15, 20 years ago, the basic assumption was that you first test any kind of updates before you install them. Current wisdom is that due to weaponification of exploits, whenever an update is out there, you just install it. The faster you can install it, the faster you're protected, especially in larger, more broadly spread attacks. One option could be, when you want to prevent known malware, to install an antivirus or use built-in ones such as Windows Defender. This is more and more frowned upon. We're going to talk about this in a second. It's no longer as effective because campaigns are very short-lived. And antivirus is an additional attack surface, right? Why is an antivirus an attack surface? It must run at very high privileges, right? This runs at the innermost, most trusted part of your operating system. And it unpacks everything, right? So there's an extremely high risk, extremely high complexity, and extremely high risk of bugs at the highest privilege of your system, right? From a design perspective, this is not a great place to be. Why are campaigns short-lived? So I'll give you a little bit of context on that because likely you don't know. Malware campaigns have changed. In the 80s, a virus or malware spread by a floppy disk, right? I gave you my floppy disk with the latest game. You took it, you installed it on your system, you passed it on your colleague, you passed it on to the next colleague. So malware spread from disk to disk to disk, from system to system to system. And similarly, update intervals were somewhat challenging. Malware lived for months to years, going from one system to another. And the idea of antivirus born in the 80s was that we distribute signature lists that we can then compare against these different malwares. With the idea of, based on all these lists, they're being shared. When you buy the antivirus once a year, you get a newly updated list, and there's a lot of malware that is around, and you can be protected against, and everything will circulate. Now, this has moved quite a bit, right? Malware campaign. If you receive malware in your inboxes, the minute it arrives in your inbox, very likely the malware is detected by 1, 2 out of 60, 70 antivirus systems, right? You can upload it to VirusTotal and analyze on how many engines detected. But after 3, 4, 5 hours, the majority of engines will detect it because they're sharing information. Now, this also means that for you as an attacker, you have to make sure that you're creating new malware that is distributed to the systems, to the hosts, before the antivirus engine is updated. And your antivirus engine will update once a day, once every 2 days, or whatnot, right? So on one hand, you have the cost of distributing the malware signatures to all your users, to all the different systems that are using your antivirus. You also have the cost of analyzing the malware, right? Whenever there's a new malware that comes in, somebody at the antivirus company will have to look at the malware, analyze it, reverse engineer it, create a signature, add that signature to the database, and distribute the database to all the customers. So this adds a day or two of latency to it. Now, a malware campaign lives for 4 to 8 hours, right? Which means that by the time that the signatures are updated, the malware campaign has already moved on and is distributing a different set of malware. Which means that the antivirus is only useful for malware that has been laying around for a while. So you can use this somewhere in the perimeter, somewhere on your mail server or whatnot, to filter out malware and attachments that are being sent. But it's getting less and less useful over time. Another better approach to prevent malware is to install applications from somewhat trusted sources, such as a market or packet manager or something like that. You can also try to prevent unknown malware, prohibit users from installing applications they downloaded somewhere from the internet, or restrict write access to directories that contain documents, not programs, prohibiting users from installing applications overall, right? We're speaking about corporate environments here, not about your desktops. In a corporate environment, this makes total sense. For you privately, if you choose to install a pirated version of a game, that's your choice, right? But you have to accept the risks that come with it, and then anticipate that. As a second step, you would like to prevent privilege escalation. So for example, verify that all access rights are correctly set on programs and libraries. Make sure that all the programs are running at the minimum set of privileges they actually need. One issue could be a program that is run by system is writable by any user, allowing the user to replace this program and then through the malicious program escalate their privileges. Make sure that all programs are patched to fix known vulnerabilities and continuously update. Make sure that the hard disk is encrypted. If not, attackers can boot from USB and have full access rights to all the files. That's one of the reasons to have full disk encryption also on desktops, right? If an attacker gets hardware access to your system, and they can reboot using CD-ROM, USB stick, or some other external media that they plug in, they could get access to the file system if it is not encrypted. Another angle is protecting history through logging, which allows you to go back and think about how you were compromised, and also look at the angles of how you were compromised. This allows you to keep a form of an audit trail, right? These logs are an important aspect of network security, and you should configure your logging services to send logging data to a trusted service. Think one more layer inside the onion if you're working on the onion system. This allows you to identify security incidents, monitor for policy violations. For example, user A is suddenly logging into this other system. Non-repudiation control, giving you viable proof of when a user logged into a given service and allowing them to check and validate that this is okay. And yeah, in the event of an attack, it allows you to go back and see at what connections were made, what the potential entry sources were. And as you know, you will get hacked. Therefore, having logs allows you to document how you were hacked and learn from your mistakes. Typical sources of logs are firewall, proxies, IDS, and whatnot, client and server machines, mail servers, database applications that all create massive amounts of logs, and you can parse these log files as you go through. For example, this part here is a little snippet from my web server where a whole bunch of robots have been downloading certain pages or trying to download certain pages. You also see lots of logs from different addresses trying well-known exploits and whatnot. All right, so these logs allow you to document what is being done. This is the example of a web log. One note and one thing that you should never log is password. So when there's a failed password attempt, don't write into your log file, there's been a failed password attempt. The password used was ABCD15, because this already leaks quite a bit of information, as oftentimes the user mistyped the passwords and it's just one letter off. And if somebody gets access to your log file with all the almost correct passwords, this is an interesting source of information. As Twitter learned about 6 years ago when they dumped a whole bunch of password information. There's a bunch of other things you should never log, such as religious, ideological, political, or trade union-related views or activities, health information, social security measures. There's lots of special protection around that, administrative or criminal proceedings and sanctions, and a bunch of other things. For example, the digital health file with all the vaccination record that Switzerland had, that was perfectly vulnerable and allowed pretty much everybody access to all this information. Does anybody remember this saga? 1, 2, 3. Yeah, that was a very fun story. Not a proud moment of Switzerland, but yeah, that happens as we see all the services are being hacked. Internet access log should only be logged anonymously. Nominal analysis of internet access is only allowed if there are tangible signs of abuse. Right? So this also limits what you can log and what not from a legal perspective. Now, I heard the gong. We've got 7 slides left. I would suggest I continue for 15 minutes and we end earlier. Cool. Which gets me to the, I think, last topic, protecting data through backups, right? Backups are the best possible way to protect your data. Because remember, you will be hacked, right? So the only thing that allows you to recover from a hack is a backup if you actually have your data. You can reduce the probability to be hacked, but you will be hacked. And to recover from the hack, you need a backup. Now, an interesting timeline here is like GitLab was hacked a couple of years ago. In January, there was an attack against the GitLab database. DB replication stops. Somebody removed DB cluster by accident. Terminates the removal, but 300 gigabytes of data is already lost. They figure out that regular backups are only done once every 24 hours. Some parts are not backed up at all. Now, after some back and forth, GitLab manages to restore from a 6-hour-old backup, but a whole bunch of other data was lost. Now, a 6-hour-old backup is better than no backup, but there's a whole bunch of risks in there. And it kind of points to the backup strategy. So from one perspective, this was a win, right? Because GitLab managed to recover a lot of the data. From another perspective, this was a loss because there was a successful attack that reduced the service, and a whole bunch of bad things have actually happened, causing loss of quite a bit of data. Now, when you're designing a backup strategy, there's a bunch of aspects that you need to consider. First off, there's different backup types. There's a full backup that just backs up everything, every single file as a plain copy. There's incremental, where you're only backing up data that has changed since the last backup. And differential, the data that changes since last full backup. The 3-2-1 rule, which is a common rule for backing up data, is that you should have 3 copies of data in on at least 2 different types of media. For example, you want to back up on a disk and a tape, and one of those should be stored off-site. Usually the further off you go, the more long-term is. So once a week, you move a backup off-site, which is a high cost. This would be like a strategy for an extreme disaster, where your data center has burned down. Right? And this can actually happen. there was an extremely interesting incident at a large cloud provider where a huge bird flew and landed in a power converter, causing a shortage, a fire, and then a whole data center burned down. Right? It's an extreme, like, freak event, but if you have all your backups in this data center, it sucks, right? And you need to be able to recover. If you spend a week recovering from that, that's perfectly okay, because it's highly unlikely. Oftentimes, you just want backups between, like, from rack 1 to rack 2, so they are a bit separated physically, and once a week on a different medium or whatnot, right? So you want to scale that. And most importantly, you also want to test your backup strategy, so if you can actually recover the data from each of these different places. Backups are made differently depending on the type of data. For virtual machines, allowed to restore a machine without having to reinstall and configure all the software. This would be ideal, right? So you have a snapshot of the image that you can use. If you are backing up databases, they have their own tools to back up, restore the content of their database tables. Use those tools and integrate them into your backup strategy. It's not sufficient to just back up the raw files on the disk. File storage, on the other hand, the data storage servers can archive every version of every file up to the last backup, such as 1 day, so that no data is lost if files are accidentally deleted during the day. This gives you a nice backup strategy, and then you do the regular backups on the daily, weekly, monthly basis, depending on the schedule. Disaster recovery plan, right? Making backups is not sufficient. I already alluded to that. Backups need to be tested regularly. So you need to actually test if you're able to restore the backup from disk and reinstall the systems and ensure that you can recover from the backups that you're actually making. So you need to develop a disaster recovery plan where you record in detail all the individual steps how to rebuild a system in case of a major failure. Right? Same as for a power outage. So oftentimes in day-to-day business, you're updating servers, you're updating systems, you're never restarting the system. So for example, if you have servers that form a circular dependency from the authentication server to the mail server to the backup server, where the backup server only has access to some of the files if the authentication server gives the okay, and then all the servers go down and you need to restart them, right? You need to figure out a startup procedure for all these services at any given point in time. And all of that needs to be documented in the data disaster recovery plan, right? If a server goes down, a data center goes down, or all your data centers go down. And you need to have, like, the special mitigations in place to recover from all of those. Cool. Let me conclude and summarize some of the aspects we talked about today. Security has to be implemented at many different levels. So you have to verify completeness at the network level, at the desktop level, at the switch level, at the firewall level, at the service level, and whatnot. Many things can go wrong if there are people with malicious intentions, both internally and externally. So we're aiming to prevent bad things from happening while letting people do their work. We're trying to enforce principle of least privilege as a core idea, and limit the harm they can do, but give them the power to do as much work as they can. Most measures, such as zones, firewalls, proxies, VPNs, and so on, are preventive, right? They are trying to prevent illegal access. Antivirus, web application, firewalls, IDS, and so on, they are detective controls. They give you a signal that something bad is happening, and often require humans in the loop to act on this information. So you need to design your security operations in a way so that you can react. Logs and backups do not prevent or detect. They are corrective methods, like after you're hacked. They reduce the impact after something bad has happened and allow you to recover and continue your business or your operations. That's all that I had for today. I'm going to stick around for some more questions. Otherwise, I'm going to see you next week. Thank you, folks.